Is MSE 5033 Composite Materials lecture number 9. And in this lecture, we will talk about toughening theories of composites. Um, Fracture mechanics is the basic theory that you can use to understand the toughening theories. But there is a lot more to be covered under fracture mechanics that you can learn from another course. But the basic fundamentals of toughening in composites will be covered in this class. But for that, you need to understand what is fracture criterion for various materials. So, what is fracture criterion? You may remember from your material science fundamentals where you understand that even though a material has got a certain strength, it still has a certain probability of failing at a load that is much lower than that defined by its strength. And that is because of the way a crack propagates through the material, and while propagating, it is stopped by the material, by the surrounding material around that crack. And for that, we use what is called a small scale yielding approximation. So assume that this is the crack and there is a range around that crack which is called a plastic zone. And even around that, a slightly larger area is called the K zone, where the fracture toughness of that area is going to be important. Now, this plastic zone and the K zone are going to be directly correlated to the fracture toughness of that material. So what is fracture toughness? Fracture toughness of a material is the ability of a material to withstand impact and withstand energy of that impact, and how that energy of that impact is stopped in its tracks is dependent on its fracture toughness. So there is something called stress intensity factor K, and in that K zone that is going to control how that crack is going to be able to push its way through and get out of that K zone. So how does a crack advance in a material? And where did all this come from? I mean, there has been these studies for a long time, but it really became important, especially when we started using ceramics in the mid 80s. I mean, there was a lot of projects being funded by the Department of Energy and all those, different kinds of agencies where they said, how do you improve the performance of an engine? They said, you got to be able to burn the fuel at a much higher temperature so that most of it is converted to energy rather than gases that have to be disposed of. So in order to do that, you have to use materials that can withstand much higher temperatures. But what they quickly figured out is that if you have these materials, they have to be able to withstand the impact of the application. So for example, if you have a ceramic engine in your Chevy or your Corvette or whatever, and you're going at 100 miles per hour and you get into an accident, if your ceramic engine is going to break up because it is extremely strong but brittle, it is going to break up into 100 different parts. How do you put all that back together and start driving again? So then they figured out that you have to introduce some form of toughening into the material. So that's where all these studies came from, especially regarding ceramic composites. So for that, you have to understand what is called the K zone around an advancing crack. And suppose the K zone is pretty large and all the stresses are governed by the K factor. And what we understand is that that crack will advance beyond this K zone if all the bonds in that area can break. And how much is that energy that you require to break those bonds? And that is governed by the forces acting on the boundary of the K zone. For example, if there are a lot of forces acting on that K zone. For example, everything is being pulled apart. Okay, so that is the energy that is acting on that K zone. And so the crack will advance if it has enough energy to break all those bonds within that K zone. And I'm not going to derive all this, but what you need to understand is that there is a critical factor K1C. And why it is 1? Because there are 3 modes of fracture for any material. The first mode is tensile mode. The second mode is a force in the second direction, that is normal to the tensile direction. And the third mode is shear. And among all these different modes, the tensile mode needs the least amount of energy to break a material. So the K1C factor is the lowest for the tensile mode. So most of the time, if we can design a material for the stress intensity factor K1C, then the material is expected to withstand all the other forms of failures. Now, K has to exceed a factor K1C, and the plastic zone has to be much less than the K zone. And this whole concept is, most of the time we only study this in terms of elastic fracture. Okay, so we call this whole area of study as linear elastic fracture mechanics. But unfortunately, the solution is not really entirely linear elastic, because for the plastic zone to be extremely small with respect to the K zone, K has to be equal to K1C. And the K1C is the fracture toughness in mode 1 and the critical fracture toughness in mode 1. And what we understand is that it is a material property that you can design for and calculate and test for. In actual materials, say like aluminum or copper or steel or whatever, most of the time they have low yield stress. So they have an extremely large plastic zone. For example, rubber. Rubber can absorb a lot of energy, which means that its plastic zone is extremely large. So, I mean, this could be a little confusing to you, but what you need to understand is that in this material, we want this plastic zone to be small with respect to the K zone, which means in this zone, just around the crack, there is a critical stress intensity factor that you need in order for this crack to be pushing forward through. And when the materials have extremely low yield stress, they have a very large plastic zone. And so what we are trying to do in ceramics, you have an extremely small plastic zone because they do not plastically deform. So when you are making a material into a composite, say in a ceramic or whatever, or in a polymer composite, what you are trying to do is you are trying to increase the plastic zone with respect to the K zone. And that is what you are trying to accomplish in composites for improved fracture toughness. So, what are some fundamentals of fracture mechanics? You need a loading mechanism to advance the crack. So, if the crack has to move forward in a material, you need to be able to apply a load. So, suppose you assume that that amount of displacement that you need is equal to du, and that du does a certain amount of work which we term as dw. In every material there is a certain amount of elastic strain energy stored in that body due to the stresses and strains built up inside that body, and you need to work against that in order to advance the crack, and that work done on that body is W. Okay, so how do you get W, which means that you have to integrate that over the entire volume. I hope I'm not confusing you guys, but what you need to know is that you need a certain amount of energy in order for the crack to go forward, and that energy is going to be directly proportional to the fracture toughness of the material. So suppose you need to advance the crack, it probably will need only a very small amount of energy. So suppose you want to make the material tough, what do you have to do? You have to increase the amount of energy that is required to move that crack through the material. That means it has to become extremely tough for this crack to advance from this point to this point. How do you do that? If you make this material extremely tough, extremely strong, it will need very low amount of energy to push its way through. But suppose you make the material weak around this crack, or make this soft around this crack, that means it gets squished and stopped from moving forward. You understand? You need to increase the energy for this crack to move through this area. That's what you have to essentially do. Okay? Now, there is a critical amount of energy that you require to move that crack by a certain distance. And that energy has to be dissipated most of the time as heat, which will all contribute to the crack generation. For a crack of size A to advance by a certain value dA, a small value dA, you need a certain driving force. And how do you increase the toughness of the material? You have to increase the amount of energy that is required to move that crack. So you can define this in terms of energy release rate, or you can also define this in terms of fracture toughness values. Okay, so what is the driving force or the energy required to move that crack? It is defined by this relationship, which is dW, which is the work required to move that crack by a certain distance dA, minus the amount of elastic energy divided by dA. And this value du elastic over dA is a negative number. Please don't ask me to derive it right now, but please understand that that is what it is. Okay? So, in order for this strain energy stored in the body to be reduced in order to advance the crack, this should be reduced in order to advance the crack. Okay? So, the other part of the resistance to the crack growth is the value R. Okay? So, that R is defined in terms of D of the energy of the crack divided by the length of the crack moving forward through that small length of that crack. So equation 1 and equation 2 have to be equal in order for the crack to move forward. So you are essentially, there is a certain amount of resistance to the growth of the crack which is pushing against the crack, and there is energy of the crack that is trying to push its way through. So both these are equal, and if one of the other, if G increases over the resistance, that means that that crack will push through. Do you understand? So let me repeat here. So there is a certain amount of resistance to that crack R that is stopping the crack from moving, and there is a certain amount of energy, driving force or driving energy that is pushing this crack through. So in order for this crack to start growing, the value of G has to slightly exceed the value of R. So the necessary condition for advancing the crack is that at least G has to be equal to R, and that value is called G1C, or the critical value of G in mode 1. And G is determined by the applied loads, and R is the resistance force required to stop the cracks, and G is the R is the resistance and G is the driving force. So they both have to be equal, and they have to be at least equal so that either the crack will be stable and stop, or it will start moving. And it is possible to apply this to both edge and center cracks. If you remember from your fracture mechanics fundamentals, there is a certain amount of stress that is required in order for a crack to grow, right? So this is essentially a different way of defining that relationship. And so you might remember the relationship between fracture toughness. So what is the stress required to move a crack of critical length A? It is equal to, the stress is equal to K1C over pi under root AC, right? Or I believe, yeah, I forgot the exact relationship, but I will try to remember that and tell you in the class, okay? So just a minute, let me find out and tell you that right away. Yeah, I'm trying to figure out the exact correlation. I'm trying to remember the equation for that. I might be. Okay, yeah, that's um, so. Yes, you are. I mean, I was right. So fracture toughness K1C is equal to a constant Y times sigma fracture, which is a stress required for the fracture, times under root pi times A, or K1C is equal to, sorry, sigma F is equal to 1 over a constant times K1C divided by under root pi A. Please go look it up, the relationship for fracture mechanics, and that should tell you that. Okay. So, and there is a clear correlation between fracture toughness K1C and R, and they are equivalent under certain conditions. So, because composites are created to toughen and strengthen, a majority of the effort is to toughen against crack formation and crack growth, especially in the case of ceramic composites. And especially for ceramics and ceramic composites, there are many different toughening theories, which I actually posted the Roy Rice papers. But there is also another paper by Marshall and Ritter. You can take a look at that, and they talk a lot about what are the different ways of um, creating toughness, and some of those are counterintuitive. Okay, so you are actually trying to create a micro crack or a set of micro cracks around a crack. So what are you really trying to do there? You are actually weakening the material around the crack, so it's becoming like rubber or like a fluid around that crack, and that fluid will kind of blunt the crack from moving forward, if you will understand what I'm saying. And same thing they do in the case of transformation toughening. So where is transformation toughening used in ceramics? I hope none of you have a zirconia uh, tooth insert. If you have, that's what it does. So that is one of the reasons, even though ceramics by themselves are not very strong and tough, but because of the transformation toughening that has taken place, so they add some additives that makes the material extremely tough through large scale volume change, and that is the process of transformation toughening. And then the most important toughening mechanism is fiber reinforcement. So when you do the fiber reinforcement, what does it do? When you are pulling out the fibers, when you are elongating the material, when it is undergoing elongation, it is undergoing some amount of fiber pull out in that material. And when it is pulling out, it is dissipating a lot of heat and energy. So that is one of the ways in which it is toughening the material. So in this case, the some of the toughening theories, we will talk about the energy method for the first two, and for fiber reinforcement we will use the K1C method. Okay, so what is the energy approach? So we talked a little bit about that in the beginning, right? So how does toughening take place in composites and ceramics by this way? So for example, if this is a certain crack and a certain load is being applied here, okay, and how do you toughen that material? Even though they are tough in the sense that from the regular ceramics to these materials, it is tougher. So it might be like, it might have a toughness of say 2 or 3 megapascals root meter. Please remember that the units for toughness are megapascals root meter. So if it is like, 3 to 5 megapascals root meter, even if it goes up to say 5.5 to 6 megapascals root meter, you can say that it has toughened by quite a bit. Okay, so these are tough, brittle materials, but still you can toughen them by a certain number. Okay, so what happens in the process zone leads to increase in toughness. So process zone or the plastic zone. So for that, let us imagine that the crack tip is advancing. There are 3 separate ways in which to get toughening. Okay, so suppose you have a polycrystalline ceramics or ceramic composites processed by sintering. Okay, and in this process, around this crack, you have created a series of micro cracks formed by the concentrated action of the stress inside the grains ahead of the advancing crack. So these are the 2 zones. So this is called the plastic zone or the K zone, or no, plastic zone, and K zone and the plastic zone, right? So what you do is, in that small region around the plastic zone, you are creating a series of micro cracks. And that region between the plastic zone to the K zone is called the process zone. Okay, so you have created a set of micro cracks around this area. So if the crack is going from 0.3 to 0.2 to 0.1, what does it do? It locally reduces the stiffness of the material and lowers the elastic modulus of the material around it. Okay, so in this process zone, you have a lower elastic modulus of the material than in the rest of the material. And in order to create those micro cracks, it uses up a lot of energy. But the unfortunate part is that it is not very easy to control the micro cracking. So when it does that, it toughens the zone around this crack. So which means that it becomes almost blunted, or it is not able to move forward from this point to this point. So that's what, so even though you are toughening this material, making this material weaker with respect to its elastic modulus, you are actually making the material tougher. So please understand, there is an inverse correlationship between elastic modulus and fracture toughness. So because you cannot really control the micro cracking, we use fiber reinforcement as another toughening technique. So there are many different types of fiber reinforcement. The most common one is short fiber reinforcement. And so what are they? These fibers or fibrils are approximately 10 to 15 microns in diameter, approximately 50 to 60 microns in length. These are silicon carbide or alumina fibers. They could be short fibers or whiskers. and you combine the whole thing together and sinter the powder whisker compact. So what does it do? By the way, whiskers are not a preferred mechanism of toughening anymore because of the problems with things like silicosis or berylliosis and so on. So you don't want to use that anymore. So, but you can add short fibers to toughen the material. And you can see that the aspect ratio of these fibers are only approximately 4 to 10 maximum. And so there is not a whole lot of toughening that can take place, but it does improve it slightly. So what we do is we do fiber reinforcement and you lay up the fibers in a matrix. So we talked about two-dimensional fibers, and those two-dimensional fibers can transfer the stress from the matrix to the fibers, and that also increases the stiffness. But the principle used in ceramic composites is different from that of polymer composites. So when you do fiber reinforcement, what they do is, in ceramic composites, they put a very weak interface between the matrix and the fibers. So the fibers are not very well bonded together to the matrix. So as soon as the crack moves through or moves close to the fibers, it breaks the interface. Then these fibers are free to move up and down that area in which it used to be held together. So when that happens, it dissipates a lot of heat and it slides against the fibers to let this happen. So there is a lot of frictional energy that has to be used up in the process. So that frictional energy will weaken the area around that crack. So it reduces the yield strength of that area around that crack and it increases the toughness around those fibers. And this is typical of ceramic composites. But in the case of polymer composites, you are transferring the load from the matrix to the fibers. So that also uses up a lot of energy, which will in turn increase the toughness of the material. So in ceramic composites especially, there is a critical value for the fiber to matrix bond strength or the interfacial strength. And that has to be just right. And that is achieved by controlling the interfacial thickness. So typically in ceramic composites, if the interface is made out of pyrolytic graphite or or some kind of nitride, boron nitride, what they do is they are typically of the order of less than a micron. If it is more than a micron, it becomes extremely weak and it will crack in no time at all. So you do not want that to happen. So that fiber to matrix bond strength must be just right. If it is not too strong, the fiber will simply crack and there is no fiber reinforcement effect. But if it is right, there is low friction. If it is too weak or if it is too strong, then the fiber will simply flop around the inside the matrix. So it has to be just right so that it can dissipate enough amount of heat inside that area. So fibers have to be relatively strong. So in this case, you use micron diameter fibers, and because the critical flaw size in those fibers are of the order of more than a micron. So if the microns, if the fibers are more than, are of the order of a couple of microns, then the chances or the probability of finding a flaw inside that fiber is much, much less. So they are extremely strong compared to the matrix. They have to be eventually able to break, um, and the process zone is the bridging zone. So the process zone is the area in which the fibers are holding the whole thing together. So there are certain areas where it has broken apart, but certain areas where the fibers are still holding together. So when you do fiber reinforcement, it increases the uh, fracture toughness by quite a large extent. If you take just the matrix itself, if it is of the order of 3 megapascals root meter, and the fibers are of the order of 10 to 12 megapascals root meter, that fracture toughness of the whole composite becomes approximately 10 to 12 megapascals root meter. The other way of toughening a ceramic is by a process called transformation toughening, and that is found in zirconium oxide type of material. And this was uh, done by Tony Evans and Kathy Faber. I mean, Tony Evans's paper was one of the first papers that I posted for you guys to look at. So there might be something listed there in that paper. So please take a look at that. I mean, the Ceramic Society presentation, final presentation paper, or the annual conference paper. He has talked about this. So please take a look at that. If you don't remember this, please go and take a look at that again. Okay. So what is the process of transformation toughening? Pure zirconia exists in three forms. In the high temperature form, it is cubic, about 2400 degrees centigrade. In above 1500 degrees centigrade, it is tetragonal. And monoclinic is below 1200 degrees centigrade. And there is a volume change associated with all these three different forms of zirconia. And there is polymorphic transformation with volume change. So what we are doing is we are playing a game with this material. So you add about 5 to 10% of magnesium oxide. It produces metastable precipitates of tetragonal T phase at room temperature. They are not thermodynamically stable. Okay, so there are a lot of these particles formed at room temperature. And when you apply a stress on this material, these are forced to transform from tetragonal to monoclinic. And it is a stress induced transformation. And during that process, so there is a lot of volume change associated with it, and it provides the toughening due to the transformation strain. So you are only forming about, you are forming about 40 to 45% monoclinic. So there is a lot of toughening taking place in this material because of the transformation due to the stress. So for example, if you're in your teeth crown, if it is made out of zirconia that is stabilized, partially stabilized, either yttria or magnesium oxide stabilized zirconia, what happens is that because of that volume change, it can accept the stress that is being put on our teeth. Okay? So then the ceramic doesn't break. And then once you release the stress, it goes back to its old structure, tetragonal structure. And if you are chewing on your teeth, then it gets transformed to monoclinic, and that monoclinic transformation gives it enough toughening. You understand? One thing to note is that I mentioned that in the last class, fiber reinforced composites, if it is being compressed, it can undergo buckling. So if it is straight, if the fibers are straight, then it is unbuckled. Um, so there are two different ways of buckling it. So you can, and if you have not put them in the right format, then also it can buckle. So just a minute, let me quickly look through. So this is also a way in which you can calculate the force that is applied around these fibers. Okay, so by doing that, you can calculate how much force is applied on these fibers and how much force is applied during the processing of the composite material itself. You can calculate that by using the force that is required to pull out one single fiber. Okay, so this is a schematic of the fiber pull out, and there is some amount of debonding that is taking place. So here the pull out has already taken place, and here the crack is moving forward. Okay, so as it is moving forward, the fibers are pulling out, and then they are breaking apart and so on. So it is slowly dissipating a lot of heat in the area around the crack. Okay, so this is a schematic, and this is the actual picture. If you look at it, you can see the amount of pull out that has taken place. So this is boron aluminum, and there is a lot of interfacial stress that is generated during the actual pull out itself. Now, as a function of the fiber length, there is a certain amount of work that is required to be applied in order to pull out these fibers. So this can be plotted schematically as a function. So how much work do you have to do in order to pull these fibers out? So beyond a certain length, the work of fracture goes down. But till a certain length, you need to apply a lot of work. And that work can be represented in terms of the stress that is required in order to dissipate the energy that is being applied during the actual fiber pull out. So you can see the amount of, so here the fibers have been pulled out, but there are certain areas where you can see the fibers that are partly pulled out. Okay, so this is in the case of aramid epoxy composite, and you can notice the fibrillation in the fibers. So there is some amount of fibrils that are around the fibers, so that also adds to the extra toughness in the material. So those fibrils have to be pulled out, so you need to apply extra force in order to pull out the fibers. So you can actually calculate these are schematically calculated. So depending upon the fiber length, they have a mean fiber strength. So these are certain values that are calculated as a function of the fiber length. Okay, so these are slightly different. I mean, I'm not expecting you to remember this, but just understand that there are certain values that you can calculate using these uh, applications. Okay, now especially in ceramics and composites, there is a statistical parameter called Weibull modulus. So what is Weibull modulus? So if you take two samples and you test them, you make that into a bundle and you test them. So one sample breaks at a value of around 500 megapascals. Another one breaks at around 750. Another one breaks at 1250. Now, are you going to say that the average is the average of 525 plus 750 plus 1250? Or do you want to represent that most of my samples broke at around 1250, so this is a very strong material? What would you do? You would like to process the material such that most of the samples will break at a value of around 1250. So more samples breaking at a specific number. It doesn't matter whether it is 500 or 750 or 1250. As long as most of the samples break at a value that is close to a single value, that is a good thing, because then your processing is consistent. But if your processing is not consistent, then that means that you are going to get extreme variation in the strength of these materials. Okay? And you do not want that to be the case. So if you have not really processed it properly, that's what is going to happen. So this is the average value. This is a normalized fiber bundle strength versus variance of fiber population. So you would like all the samples to break at similar values, and that will give you a high Weibull modulus. So the Weibull modulus numbers tells you that your processing has been consistent. If your Weibull modulus values are of the order of say 4 or 5, that tells you that your one sample is going to break at 500, another sample is going to break at 1500. But if your Weibull modulus values are of the order of say 20, that means they are most of them are 99% of your samples are broken at a one specific value, close to a specific value. So the standard deviation is as low as possible. Now, when the fiber breaks, it creates a stress distribution. So if that is the case, you can actually schematically represent that in this format. So if the fibers are broken here, the shear stress and the tensile stress are going to be different. Here it is all tensile stress, but here it is partly shear stress and partly tensile stress, because you need the shear stress in order to break the interfacial area. So there are multiple ways in which a composite can fracture. Sorry, this should be reinforced. So either you can have a very small break and most of the fibers are intact, or you can have a crack that is going through the entire composite cross section, where that crack will also break all the majority of the fibers. Or what is happening is that here is that the fibers are breaking, but they are still holding all the material together. So in this case, the composite strength can be plotted in terms of, so delta is the half of the uh, fractured length, okay, and sigma bar is the stress across the entire composite, is the stress across the entire composite, and sigma L, I have to see that. Uh, so needless to say, I mean, if your fiber population is going to be having a variation in strength, the composite is also going to behave in a very non-uniform manner. So it can break in and give you not very uniform strength. Okay, so in this case, if you are going to orient your fibers in different directions, say for example, if you orient all the fibers in the 0 degree direction, it will have an extremely high strength. But suppose you have the fibers all oriented in the 90-degree direction, then your strength is going to be extremely low, and it is going to be defined by the matrix strength. Okay, so and if you change the orientation of the fibers, then you remember that, I mean, like we talked a little bit about this in terms of um, the elastic modulus also in the last class. So similarly, you can also define the strength of the composite. So if you have fibers all oriented in the 0 direction, it will have almost close to the strength of the fibers, and if it is all oriented in the 90 direction, then its strength will be close to the strength of the matrix. So this is what I was telling you. Oh no, I probably talked about this in another class. So how do you define how the materials are going to behave? So this is not, I mean, so you remember the Mohr circle, right? So for composites, you don't have a Mohr circle that is a circle, okay? You have a what is called an ellipse, and this is called the Sai-Wu failure criterion. So if you apply a certain force, then you know that it has a certain tendency. So suppose your loads are, or your stresses in the one direction and the two direction are plotted here. So if you apply a certain amount of stress, then you know that you know whether or not it is going to fail or not. And this failure criteria is called the Sai-Wu criteria. And why Sai-Wu? Because he is a guy who came up with this theory. So in a monolithic material, if you have a notch, the material is going to just fail in no time at all. But if you have a composite, it is going to fail in different methods depending upon the debonding that can take place. So suppose there is localized debonding taking place. Okay, localized debonding taking place, then the crack can just grow in this region in the localized area alone, or the fibers have not broken at all and the cracks have all passed through the matrix completely. So which means that the composite is still intact, but it has created a lot of matrix cracks. The other form of crack is, suppose there is an advancing crack, it has gone through one fiber and then it hits the interfacial region between the matrix and the fibers, and it gets deflected along the fiber matrix interface. Okay, so and then these fibers are just being pulled in and out, and that will cause the energy dissipation in that area and increase the toughness of the composite material. So what are some of the advantages of composites? If you remember, I don't know if I talked about this earlier or not. So in fatigue, if you take a look at say mild steel, if you plot the number of cycles versus the stress, if it is mild steel or BCC or body centered cubic type of material, what happens? The as the number of as you increase the stress, the number of cycle actually goes down, and it actually demonstrates a hockey stick type of fatigue plot. Okay, so that is called the SN curve. So if you don't know what it is, please go look it up. If you have not heard that terminology, please go look it up. Okay, it's called the S-N curve. If you Google that, you will be able to find out. So if you apply a cyclic fatigue in your material, what happens? So you are applying a stress. So you're not exceeding the tensile strength of the material. You are applying, say, 10% of the tensile strength. Okay, and this is the zero, this is zero stress, and you are applying a certain amount of negative stress and a certain amount of positive stress. Okay, so in the mid plane, the middle of that, so sigma max minus sigma min by 2 is the middle point of that stress plot. So that is called the amplitude of your stress. Okay, and however much it is different from the zero value, it is called the sigma mean. Okay, and the sigma max minus sigma min is the delta sigma. So the maximum versus minus the minimum stress is the amplitude of your fatigue cycle. So for polymer matrix composites, so for BCC type of materials, if you plot the sigma versus number of cycles, what you will see is that it goes down as a function of stress. If you increase the stress, the number of cycles goes down to the left. It goes down like that, and then it goes almost horizontal like this. So that is called for most of these materials, it is called the fatigue limit. Okay, so if you do not exceed that fatigue limit, this material will last forever. But sometimes you don't have the luxury of doing that. Okay, so in this case, say for example, PSF is a type of a matrix. If you don't have any fiber reinforcement, what happens? If you want unlimited life for this material, you probably cannot go above 20 megapascals. But suppose you are going to say 160 megapascals maximum, sigma max. That means you need to go 40% fiber reinforcement. And even then, you should not exceed 60 megapascals. If you exceed that, then chances of it lasting beyond a million cycles is very less. So in the case of glass fiber, polypropylene composites during cyclic fatigue, if you are applying say 10 hertz, it doesn't increase the temperature by a whole lot. So beyond 20,000 cycles and at 20 hertz, you can see that there is a almost 12 degrees centigrade increase in temperature in the material. Okay, so that also happens, and that happens because the amount of friction that is introduced into the material due to the cyclic fatigue. And what is cyclic fatigue? You are like a wing structure, or even our own human body. When we talk about getting fatigued, what is it? You are applying a stress, a maximum stress and a minimum stress in order to in a cycle. Okay, so and these are the number of such cycles. So after 20,000 cycles, or even after 6,000 cycles, the temperature has gone up by 12 degrees centigrade during this process. So this is how an SN curve for metal matrix composites are going to look like. Okay, so if you add alumina in aluminum at room temperature, okay, you can see that it has got almost a flat line. Okay, so if you apply say approximately 50% or 60% of its tensile strength, it can last forever. But suppose you increase the temperature to 260 degrees centigrade, then it actually comes down, starts coming down. And compare that with magnesium alloys, just alloys. So if you fiber reinforce a material, its fatigue resistance increases tremendously. So just aluminum alloy at 260 degrees centigrade, you see this one. It cannot go beyond say 10% of its tensile strength. But suppose you reinforce that with 50% alumina fibers, you can easily go above half the tensile strength, almost close to half the tensile strength. So that is the advantage of fiber reinforcement. So you can also see that, for example, particle reinforcement increases the fatigue resistance of these composites. So for example, this one is with 30% particle reinforcement. So 30% particle reinforcement, the stress goes up to say almost close to 250 megapascals. Compare that with no reinforcement. So you can't even go beyond 100 megapascals. So that's the advantage of fiber reinforcement, especially with regarding fatigue resistance. Now, if you have particle reinforcement, they are not as good as continuous fiber reinforcement. So you may find that the crack can either, if it is a coarse particle, the crack can go through the particle, or if it is a very fine particle, and the bond between the particles and the matrix is weak, then the crack can actually go around the particle. So it depends upon that. So again, you can, so what are you actually doing in a composite material? In a composite material, you are actually increasing the toughness of the composite material by fiber reinforcement. So when that happens, that's one of the reasons why the fatigue resistance increases. Now, as it is undergoing fatigue resistance, the crack is also moving forward. A crack or cracks, number of cracks could be increasing, and during that process there is a loss in modulus, and when you lose the modulus, when it reduces the modulus, you are actually increasing the toughness of the material ahead of the advancing crack, which in turn stops the crack from moving forward. I hope I am being very clear here, and I hope you understand. If you have any questions, please do send me an email and ask me questions. So this one represents the modulus loss in cyclic fatigue in silicon carbide aluminum. Silicon carbide particle reinforced aluminum material. So in composite laminates, the amount of damage is much less than in the case of homogeneous materials. That's the only thing that I want you to take away from this figure. So here you can see that, I mean, there is some fiber pull out, but some of those fibers got broken right close to the fracture surface. So these are again different ways in which composites can fail. So as it is undergoing fatigue, it is losing its modulus ahead of the advancing crack. If you apply a load of 110 megapascals, it is stable up to a certain extent, but then suddenly it starts failing because the cracks have advanced beyond a certain stage. You can actually plot a parameter involving peak stress and the rate of modulus loss. So the more the modulus loss, the tougher the material will get. Okay, so you can see that if you increase the maximum stress, you are actually decreasing the maximum stress it can, maximum number of cycles the material can withstand. So these are the, so you can plot, this is another way of representing SN curves, that's all. The stress versus number of cycles curve, that's all, okay? So if you do not want the stress, the modulus to reduce by a whole lot, that means you can get much higher lifetime from these composite materials. But if you apply a very high stress level that is close to the strength of the material, that means it will lose its modulus quite drastically, which in turn can reduce the number of cycles the material can withstand in fatigue. In in some of these composite materials, especially in metal made composites, you can also find what is called, some thermal cycling can take place, And sometimes, for example, if you have it in a piston type of a material, it is undergoing thermal cycling. And if you do that, it can, uh, after 1,000 cycles, you won't find any this thing. But then beyond a certain number of cycles, it will start demonstrating internal damage. So you can actually plot what is called the creep curve for a composite material. So unlike a metal type of a material where you will see that um, the creep curve might be like this. It will have clearly three stages. But in the case of ceramic materials and ceramic composites and polymer composites, what you will find is that beyond the primary stage, it is very stable and uniform. And then at the tertiary stage, after a certain number of hours, then it will just take off and it will not last at all. So the secondary stage, the secondary stage is going to be pretty long in the case of composite materials for creep. And you can actually plot the, these are pretty interesting materials, especially for doing creep testing. So similar to metals, what do you find? If you decrease the stress, the creep rate goes down drastically. So this is the creep curves for, the creep rupture time for, it's not creep rupture time, it is the creep rate versus log stress. And you can see that um, these values will be different for different stresses. And this is for particle reinforced metal matrix composites. So now let's switch gears a little bit and let's stop here, and I will talk about this in the next set of this lecture.